So I'm actually going to deviate from the slides for just a minute because I was thinking about it while Walter was talking, and I realized that we didn't give quite enough background. We didn't just magically decide to do EVT fitting one day. We were working on this problem for years, and our first couple of systems, a little bit like Devi's work, actually used learning to figure out how to do stuff. And after we built our first 3 systems for a DARPA project we were working on that were predicting when our biometric systems would fail, and doing a pretty good job of predicting why, but our sponsor kept saying, but why can you predict when it's going to fail? Can't you just fix it? We started wondering, what was the underlying reason? Why were we able to build machine learning that could predict that our algorithm was going to fail? It's not the same problem as fixing the algorithm, because I can always predict that it's going to fail, but not know how to fix it. But then we started looking for this deeper theory, and that led us to this idea of EVT-based statistical failure prediction, looking at what's the underlying theory. So that extreme value theory, I believe, underlies almost all of what we do in the recognition field. Because recognition performance is almost always the boundary between one class and another. It's the maximum distance from this class to the maximum distance from that class, and where those 2 classes interact, that's what drives a lot of our performance. So EVT became something that became very important. And you'll come, as we get through this, you'll eventually see how this comes back to open set. Because open set is sort of saying, that's the farthest I can get and still be in this class, and after that, I'm out. So that's where EVT gets connected back to open set. But we're going to show you a couple of other things we got to before that. So the first of this is idea of extreme value theory for failure prediction. And this algorithm is pretty simple, and we do have a library, libmr, we'll talk about later, to do all the software, so you don't have to worry about all of it. But you get the top scores, or the bottom scores, but I'll just say top here. So you get them, sort them, and keep the top highest scores. So in this recognition algorithm, bigger is better. Get them, sort them. Now you're going to fit an extreme value distribution to the non-match distribution. Take all the things that are not supposed to be the right object, get all their scores. If you actually have a match, put it off on the side for a second. Just take all the non-matches, all the most confusing people with me, figure out what's the highest score you get with those. That's why we exclude the top score, that's supposed to be me. And then you're going to determine if the top score is an outlier from the EVT distribution. So in a biometrics problem or in a recognition problem, I have n classes, one of which is right. So I'm going to take the highest scores, take away the one that's supposed to be right, fit the distribution to the things that are non-matches, and then ask, is the top score an outlier? If it is, then we're going to say, predict success. If it's not an outlier, then we're going to predict failure. That is, I can't statistically say the top score is significantly different from the others. And that's the way often we'll do stuff, is it's significantly different. We use a CDF fraction, the cumulative distribution function of the Bible, and we actually normally use a pretty stringent test, 99.999999. And if you're not within that, then predict it's an outlier. And for a bunch of our biometrics problems, that worked out pretty well. So as Walter said, the idea of the way we're doing this is, if I have this overall distribution, right, I can think of a bunch of scores. If I'm doing recognition for an input, what I really have, even though this is my overall distribution of scores in my matching, my matching algorithm, I can really think of this as really what we call a portfolio of galleries. And if you look at the use of extreme value theory on Wall Street, they're doing a portfolio of gallery models. I really have the distribution of this input against person 1 in the gallery, person 2 in the gallery, person 3. And for each of those, I'm going to take the maximum score. That's the most, how likely is it that's person 1, 2, 3, 4, 5. And that leads me to this idea of why the extrema is, the EVT theory applies to this portfolio. So I go up here, I take the scores I get, I go through my tail analysis, just fit on the top couple of scores, do extreme value theory, and that gives me my prediction. And this comes back from a paper, which I don't remember, 2011 probably, EVT-based failure prediction. So we tested a bunch of biometric algorithms. We used meta-recognition to predict the performance of those algorithms. So we used 12 different algorithms across 4 different problems. And then we compared that to the simple algorithms, can I just threshold my score? So I have a face recognition system. It gives me a score between 0 and 100. Or a fingerprint recognition which gives me a score. I can always just threshold those and say, if my score is low, then say the system failed. Okay. The problem with that is a single score doesn't work very well. And so we found that it was always significantly better on every test we ran for these biometric problems. We've since run other problems, it's not always better, but we'll see those when we come back up. So we looked at face biometrics, fingerprint biometrics, multi-biometric fusion, SIFT and earth mover distance for object recognition, content-based imagery travel. We looked at 4 different algorithms for ICBR. In all of those cases, by using EVT, we got a much better way than just threshold and score. And one intuitive way to see this, why it's going to be the case, is imagine that I have a score threshold that depends maybe on the image size. So if the image is bigger, I always get higher scores. Well, I can't use the same threshold on a big image and a little image, even if the match qualities vary because they don't overlap in the right way. EVT, at a minimum, allows you to have this sort of dynamic threshold that depends on the distributions of whatever varies about your image, quality, size, whatever. But more important, this allowed us to actually develop a new fusion algorithm that was better than traditional algorithms in all the data sets we considered in this paper. So again, not only can we begin to predict failure, but if we think about it, if I can give you the probability of failure for a bunch of different algorithms, then when I go to do fusion, I can say, well, this one probably failed. Please ignore it. Use this one. It worked. Right? So that's a simple way of using meta recognition to actually improve algorithms as well. So to explain this, I need to explain this as a graph, which we didn't have a separate explanation for. So this is a technique we use to describe our things. You'll sort of see these weird labels over here. I can't even know if you can read that one, but it's FPFAR and FPMAR. This is what we call a meta. No, that's what we call. We have a name for this. MRAD, yeah. So it's like a DET curve or a ROC curve. This is logarithmic, so it'd be like a DET curve, except this is for meta recognition. So in a normal DET curve or ROC curve, you would plot false accept rate and false detect rate. Right? Here, we're not talking about the false accept rate of the algorithm. We're talking about the failure prediction false accept rate, which we define as I predict it failed and it didn't. Right? So that's a false accept for a failure prediction. And then we can have, with this point here, for example, means that, so here we're at point 1. So when missing only 1% of all failures, we correctly, our false prediction rate is only 10%. Right? So I can now think about, I'm going to predict if your algorithm worked or not. And 1%, if I set this parameter so that I only miss 1% of all the failures, 99% of the time when I say it works. Then only 10% of the time will I say, when I say it fails, will I be wrong. Right? So this curve gives me a way of looking at my accuracy of prediction somewhat independent of the underlying algorithm's accuracy, because I'm not looking at my ability to predict it. And for this particular algorithm, so this was using the SSR data from NIST, which is a standard data set for biometric analysis and recognition. And they had a couple of face recognition algorithms. So rank 1 recognition for the face recognition algorithm they called C. Some algorithm was 89%, and for G was 84%. For fingerprints was 86%, and for another fingerprint algorithm was 92%. So we have good failure prediction on all of them, way better than just score thresholding. So score thresholding are these black points up here. The ideal points are way down here, as you would want in a dead curve. So just thresholding on score gives you a pretty weak predictor for any one of these 5 algorithms on how well it does. But by using the score analysis, we get a much better prediction. And this is sort of like a logarithmic space. So this is a huge improvement in our performance, the ability to predict that any one of these biometric systems failed. Okay, so we were very good at dealing with all of those. And so then the next question is, well, can we do even better in terms of fusion? We'll come back to that. But we also in this paper wanted to analyze, what about some of the assumptions? As Walter mentioned, underlying the formal Fisher-Tepper theorem was the assumption of IID, and it can be relaxed. So the question is, does those relaxations apply for us? So we can look at how we do if we get rid of the size, so some of the IID assumptions, because now we're taking, in fact, highly correlated things. We're applying 2 different algorithms on exactly the same data. Those scores are definitely not IID because they're highly correlated. They're computing from the same thing. And I don't know if you can read these because I can't. Let's see. So we did some sampling. So the red line here is the one that's independent, and then the purple line down here is where we did highly dependent data where we sampled them right? And we still, in fact, instead of getting worse, as the data became more dependent, the algorithm became better at predicting the failures. So all these have greater dependence, and we have better predictions in what's going on. And that's really just because, despite the fact that the extreme value theorem used IID assumptions, if the data is more correlated, it can converge faster. It doesn't have to. So that's why we get better performance. And then we looked at the question of what happens if I use different size. So this is top 5, top 10, top 20, top 30. So as we increase the tail size, here we have 5, 10, 20, 30. As we used more and more data, at least for a little while, things got better in terms of our ability to make these predictions. So the tail sizes mattered, and independence was not a problem at all. So we'll come back to later on how do we choose the right tail size. That's a harder question. So what else can we do with meta recognition? So as I mentioned, one of the things we looked at is if I can predict failure, I should be able to do this with fusion. We actually had a paper I did earlier with predicting fusion by simply choosing among 2 algorithms. Selection, easy. But we came up with a much better way. So if the probability comes from this CDF, the CDF of the Bible, we're going to call that our W score, which I will use for the rest of the talk. So our W score is the cumulative distribution function of the Bible from the EVT fitting, and we're going to now use that as a score normalization technique. And there's our paper. This is the 2010 ECCV version paper. So given a set of scores, sort of scores from our things of some length, from a single recognition algorithm, where J is our recognition algorithm, we're going to sort and retain the largest scores. Again, bigger is better for this algorithm. The Weibull distribution, we're going to fit that to each of the different sets of scores. And we're going to skip the hypothesized outlier. And then we're going to compute the outlier's probability. And we're going to do that for each of our different set of scores for each of the different algorithms. And then we can then take those scores and, for example, sum them up. If I have 3 algorithms, I can sum them. But let's look at how we're going to do it for 2 in this case. So here we have 2 of the algorithms that we're looked at, face C and finger LI. So, and then we're going to have face C and finger RI, face C and LI, RI, and then there's face C's and G's. Yeah, yeah. So the red line here is our W score fusion, and the green line is Z-score fusion, which is very standard. Z-score fusion, you're taking the sort of standard deviation and dividing by it to normalize the scores, and then use that. So this is sort of assuming a Gaussian-like model, and this is using EVT models, and you can sort of see how big the difference is between the red points up here and the green point down here. And similarly, we have blue, the squares for blue and purple. Blue is way up here. Purple's a little bit better than where it was for green, and so on. So each of these, we get a significant fusion build in terms of this pair, right? W score is much better. The next pair, W scores are better. So for each one of these pairs, the W score was significantly better than the Z score in terms of how we can do fusion. Not here, but we've done comparisons with the sum or product fusion, a whole bunch of other things, and we did much better than with all of them with the EVT. So in terms of fusion problems, one of the nice things about this is existing theories for fusion presume consistent data. So we come back to open set. What happens when I'm doing fusion when one of my algorithms just goes bonkers? Right? It sees something that it doesn't know how to handle. Now what happens in my fusion algorithm? So what happens if somebody's trying to defeat my system by changing their data, and this is not a completely made up thing? We need an algorithm that can predict that a modality is failing and ignore it. So for example, this is Ramia Abdazi, I can't remember his name. He's a drug lord who underwent facial recognition surgery. So all 3 of those are pictures of the same guy. And if I'm now trying to recognize this person crossing the border, and I'm looking for this face, I will probably fail when I see that face. Okay? But luckily, they were also listening. They had some voice samples of this guy from phone recordings. His voice recognition algorithm can say, I know who he is, but the face recognition would say, I don't know who he is. If I use traditional fusion, I'm going to equally weight. It is, it isn't. It is, it isn't. And where it's going to end up is going to be very hard. So the idea of meta recognition for fusion is also be able to allow it to say, here's what happens when I know I'm wrong. So to do this, we actually have a related problem. Forget that it's completely wrong that they intentionally changed it. What happens when I have a really good algorithm and a bad algorithm and I fuse them? In many cases, classic fusion will make things worse, but if I take a good algorithm, so here I have the raw performance of the left index finger for matching, and down here I have the raw performance of face. Okay, so face is down here well below 0.5 and fingers up here at like 0.8. If I fuse these with very simple algorithms, so if I do classic decision fusion between the two, I get slightly better than face, but actually worse than finger. I should just throw away the finger or the face and not use it. We had a bunch of different connections of algorithms we did for this fusion, but if I were looking at these and I'm looking at sort of the delta 1-2 feature we used and the finger fusion, we get up here, okay, in terms of what we can get with meta recognition. If I use simple decision fusion, that was the blue line here, right? You can see how much difference this performance is to that. The performance with meta recognition improved over the finger LI. It only used the face when it needed it, and when the face was so bad it couldn't use it, it was able to ignore it. Okay, so this is actually a slightly different version of meta recognition. This was using features that we used in our fusion from a learning-based meta recognition technique, which allows it to do a better job of learning data dependencies. Statistical fusion is data independent, doesn't know anything about the correlations between two different sets of data. If I want to do fusion, learning that correlation can actually be a little bit more powerful than just doing two independent EVTs. But we also did this with z-scores and w-scores, so sort of coming back to if I have the face and the finger, and here we have the imposter. We really replaced in this data set a synthetic thing. We took 3,000 samples from NIST BSSR, and we literally just paired up chimeras of this person's face and this person's finger. And then sometimes we chose an imposter's face and this person's finger. And we try to ask how well you can do. So for different combinations, z-scores are significantly hurt. If I go back one slide just to remind you, right? Fingerprint alone is around 80%, 78 to 80%. If I combine face with the face being wrong and the finger being correct, z-scores drop down to 65%. W-scores go up to 81%. Okay? Because the imposters weren't always the imposters. There's a little bit of realness in there in terms of where they're going. And then so on. You can sort of see for all these different tests, the z-scores are significantly hurt by adding an imposter. And if I have only one imposter, the w-score doesn't really care much at all. It almost always labels the imposter as the outlier and ignores them. It gets a little trickier when I have two imposters. Now I have twice, so both of these imposters are matched. So both face C and face G are pushing for this one person to be the winner and this one's losing, but still we're above the raw fingerprints data in terms of where they are. So z-scores highly impacted by the failing scores, w-scores not so much. Okay, so now come back to how this is related to a lot of our recognition problems. If I think about a standard SVM or any other decision boundary, but we'll use SVMs at the beginning, right? What I'm really interested in are points that are approaching this boundary. And traditionally, if I want to do probability calibration, so that I can sort of say, here's my SVM and reject things that are unlikely, that's not quite solving the open set problem, but at least between these two boundaries, we can do something. And people have looked at calibration models for this, the most common being a sort of sigmoid from what's called Platt calibration, fits a sigmoid between this data and that data, and says that's how we're going to do it. Well, we had some problems with that in terms of both where it came from, it was just sort of put together, and we wanted to find something a little bit more supported. So we recognize that these boundaries are, again, a classic use of EVT. If I take all of the not male distribution and I look at the scores in terms of the SVM decision boundary, I'm looking at the extrema. For the actual, not males, actual women, what is the largest score we get out of this SVM? I'm looking at extrema. If I turn it around and I look at all the males and say, what's the lowest score I get from this male-female gender classifier, I'm going to also be looking at extrema. In one case I'm looking at maxima, in one case I'm looking at minima, but I'm looking at the smallest minima or the largest maxima, and then we can play some games. So we can now use this as a way of redefining or recalibrating our boundaries in terms of decisions, in terms of EVT theory, where we get the tail from the scores of the opposite class. So if I'm on the male class, I go get all of the not male scores, fit the extrema, in this case the maximum to them, and I can fit a viable to the tails. This gives us our viable, and then we get our normalized probabilities using the viable CDF, or the W score, which is given by this formula. So this allows us to normalize the scores, and we had a CVPR paper in 2012 where we use this for fusion of multiple attributes. So each attribute is a binary SVM, and now we want to figure out how do I fuse them. So if I do a search like Indian females or male and black hair like target, and I'll come back to the like target in a little bit more detail next, but I want to be able to normalize these, but I actually have two things, Indian and female. Those SVM scores are not in the same, possibly the same score space at all, so I got to renormalize them to make them normalized. And this EVM approach, EVT approach gave us a way of renormalizing them. So we want things that, oops, wrong direction, put those together. So the sort of utility of this space is highly distorted. We want to normalize it into a more unified space, and it allows us to take things where in this space, things like Indian females provided a mixed set of results, right? There's one Indian female in there. Our approach gave us much more consistent. And the problem without this kind of normalization is people who were clearly females might have had a very high female score, even a low Indian score. And when you combine them, that just doesn't mean that they work out. Here, they were renormalized among all the women. Where did you sit? And the real question is not, am I the most womanly woman? It's like, am I a woman? It wasn't find me the most classic looking woman or whatever. And the same is true when we get to more complicated things like faces as chubby and round as the image on the left. So this is when we talk about a target search. We actually want to be able to answer a more specific question. Here's an image. Find me somebody whose face is like that. Now that one might not seem like an extrema problem, but it is, because we can think of distance from a point in any space as an extrema problem, right? It is how close to zero can I get on distance. So if you're doing another kind of recognition problem where it's not the maximum but the minimum, it's still viable because it's bounded from below, and now I have a distance function, and I can use that to renormalize and get some really good results out of that. So we actually did a whole bunch of experiments where we took a bunch of different attributes. So for example, bangs and black hair, bangs, chubby face. We did a whole bunch of these, and everywhere here you see one red star or two red stars. It means that when we use this query in context, which I'll explain in just a second, we did much better than using query only. So the second thing we found, which is what this context is about, was that, and I have no idea why these came in this order, Walter. The build is backwards. Okay, I'll come back to the context in a second. So the first thing we just did is, does our query only rankings match human rankings? So we did a statistical test. Are we consistent with how humans would rank images? This sort of bullseye pattern here is showing me, if I look at the top 5, that's the inner ring, then top 10, top 15, top 20. So we did searches over hundreds or 2 million images. We looked at the top 10 scores, top 50 scores. And in most of the cases, when we did these combined searches of bangs and black hair, bangs, right, we did very close to human performance. There's a couple where there's only a blue dot, so we were not as close as we would like. And then we asked if we add context. So context here was we were having some oddnesses in these query-only results until we started recognizing that sometimes in answering the question like how chubby is someone's face or how rosy are their cheeks, the answer to how rosy someone's cheeks are depends on how old they are and what's their gender. Given the same exact color on the cheek, people will label kids with that brightness of red more likely to be rosy-cheeked than they will a man. Right? So age and gender worked out. So we had this idea of context we had to put back in, and then we became even more closely related with humans. And then we asked how often were the query and context better than query only. So all of this allowed us to do much better. So EVT, in this case EVT recognizing there were other dimensions, was much better than where we were before. And sort of coming back to that idea of, well, how do we do this target search where I chose somebody? If you actually look at around the shape, so we'll choose some image, and then given that image, we're going to look at the distribution of data around it, fit an EVT to it, and you can sort of see the black points here. Each of those are the actual occurrences of scores within the normalized space. And then we use those to renormalize a new EVT we can use to resort the data. So this allows us to then show us where a particular person is on each of, in this case, 3 dimensions, how they relate to the target query. So this idea of renormalization, a little bit of oddness, we take EVT, we normalize data. Now we can measure distance from that normalized score, which is itself another EVT, because it's a distance function on top of some other normalized score. So this is showing you some of the things we've been doing with meta recognition. We're not actually the only ones to be doing this, so we want to make sure we point out some of those. Vishal and Rama, and actually I don't know who the first student was, had a recent paper where they started using sequential score adaptation with extreme value theory. Now, all the extreme value theory we've been talking about is what we actually call extreme value theory of the first type. It comes from the Fisher-Tippett theorem, and it's based on the distribution of minima or maxima. Turns out there's a second extreme value theory, which asks the probability, how often do I exceed a particular threshold? So if I choose the value of 100 and say, how often will the temperature exceed 100? That distribution comes from a generalized Pareto distribution that looks like this. So Vishal and Rama's work looked at train tracks, doing an inspection and trying to ask the question, how often will a train track be more separated by a particular distance? Because that's when they crash, right? Wheels get too far apart. So there they had a particular threshold of interest, and now you can build another model. So if your problem is related to extrema, but it's really how often will it exceed the threshold, EVT applies, it's just a different kind, and you want to go look at that. And so this paper that just came out last year is a good example of some applications of that. Other related work from Victor and Matt Turk at CVPR 13 and two other papers, right? Either of you guys here? Oh, here you go, Victor. Hey, you want to say something about this? Okay. So they were using sampling to decide what points to use in matching by basically having a guided sampler that would look and figure out, I've got some samples, I generate a model, and I look at the quality, and then I can feed back in a loop to say, no, don't use those points in matching, use these points, and iterate to make that whole process better. And that allows them to have a much more refined model that did a better job of matching. But looking at it from a meta recognition point of view, they found that they wanted to, the algorithm was more accurate if they moved to a Raleigh, which is really a specialization of the Weibull distribution, has less free parameters. So it's e to the minus s squared. So it's missing one of the parameters we have. So the advantage is they only have one parameter to fit. With the amount of data they have, it was a much more accurate form for what they want to do. In fact, Raleighs occur in a number of other manufacturing settings. Raleigh is just a special case of the Weibull, so it's not outside of the realm of EVT. It's just an EVT with one less parameter, which is often more accurate for them to fit. And from that, so they use the estimate of sigma, shows up down here, from the closest tail of scores, the closest S scores, using a maximum likelihood formula. And this allows them to get a good fit. And I will say that we've seen lots of our own experience with Weibull fitting. There are some times when this thing is just numerically unstable during fitting. You got to be very careful what happens. Even if you run our library, which we work pretty hard to make it relatively stable, there'll be times when it will just blow up on you. And that's often because you have too many points that are either too close together, or you have too many points that are really, really close to zero, and numerically the algorithm just breaks down, and it'll give you error messages and whatever. And very often, in fact, the first versions of our library just added a large constant to move things away from zero, which was a bad idea, because it changes the fitting a little bit, but it also made it so it didn't blow up as often. So the newer releases fix that problem. But so if you look at sort of the densities involved in this key point fame matching process, again, this is a natural extreme value problem. You have correct matches and the incorrect matches, and you're really trying to model some of what's going on here in the tail. The Weibull, because it's focused so much just on the tail, is strongly peaked right around the edge of the tail, whereas the Raleigh distribution is forced to include zero, and so it's a much broader distribution around those two pieces, and the fall off is generally a little bit smoother. The Weibull, when you have a small tail size, tends to be very abrupt, because it's going to have to fit among all of the final data. But maybe more importantly than the fit is looking at sort of how it performed in terms of accuracy. So in these plots here, I don't know if you can see the green line. Can anyone see the green line? Victor can, he's seen it many times. But so like, for example, here's the Leuven fitting, right? There's the green line here. This is the Weibull fit, and the blue line, I think, is the red line, sorry, red line. Red line up here is the fit with the Raleigh, right? So in most of these cases, the red line is much better than the green line. In some cases, they're very close. Okay, but overall, by switching to a Raleigh, Victor's able to get a more consistent, more accurate fit for his meta recognition. But at the concept level, it's still a meta recognition. The goal is to predict that this is failing, okay? And if it is, then they can do that. And I was going to point out to Walter, because I just was looking through the proceedings before I got here, there's actually a new paper here at CVPR on using decision scores to predict failure of their object detection algorithm, though it doesn't cite us, so. So we want to switch over to the next part, right?
Yeah.